So continuing further, the module 5 material science, and wherein we had looked into semiconductors in the previous part, and now continuing there itself with the semiconductors, we will see the expression for electron and hole concentration. Then we will learn about the relation between EF and Eg, Fermi level and energy band gap, and the expression for conductivity in semiconductors. And finally we see the definition and a derivation of Hall voltage and its relevance. Now let us see the expression for the hole concentration and electron concentration. Equations are given here. We don't have derivations in a syllabus, but you need to learn this equation. Okay, so hole concentration NH is equal to 4 into root 2 divided by h cube into pi mh star kt to the power 3 by 2 into e to the power minus ef by kt. Okay, and for the electron concentration it is 4 root 2 divided by h cube, then pi mh star kt to the power 2 by 3 into e to the power ef minus eg by kt, where me star and mh star are effective masses of electrons and holes respectively. K is a Boltzmann constant, T is in Kelvin, that is temperature, EF is a Fermi energy, and Eg is the energy band gap. Okay, that is what is combinedly given here in this slide. You can pause and view it. So we have the equation for NH and Ne here, and in the case of intrinsic semiconductor, we already know that Ne is equal to NH. So then if you equate these two equations, you are going to get as this equation, that is Me star to the power 2 by 3 into e to the power ef minus eg by kt is equal to mh star to the power 3 by 2 into e to the power minus ef by kt. That if you simplify, you are going, let us get it in terms of e to the power 2ef minus eg by kt is equal to mh star divided by me star to the whole power 3 by 2. Okay, now for this equation, let us apply the natural logarithm. So that is ln we are applying. So that means we know that we will get rid of this e here. So left hand side will be 2ef minus eg divided by kt is equal to, on the right hand side, 3 by 2 ln of mh star divided by me star. Same equation I have given here at the top. And then you rearrange to get the expression for EF. Okay, so EF is equal to 3 by 4 KT into ln of MH star divided by ME star plus EG by 2. Okay, now for all the practical purpose, we just assume that ME star is equal to MS star. So that means in the equation ME star is equal to MS star, so that means they are cancels each other. Then it is ln of 1. Ln of 1 is nothing but 0. So that means this entire term is going to be just 0. Okay, so that is what ln of 1 is equal to 0. So then EF, what it reduces finally is EF is equal to EG by 2. That's all. So what is the conclusion? Conclusion is Fermi level for the intrinsic semiconductor lies in the middle of the forbidden gap, which we also seen previously. So conclusion of that derivation is given in the figure. You can just pause and understand the mathematical equation in the figure. Now let us obtain expression for conductivity in semiconductors, both in intrinsic and extrinsic semiconductors. Now we could remember this in one of the classical free electron theory classes. This was a conductor with current I that is flowing, having a cross-sectional area A, and Vd is the drift velocity. Then current is given by Ne Vd into A. Okay, so the same one we are writing here for semiconductors. So here for a semiconductor has both electrons and holes. So first let us consider the conductivity for electrons. For electrons, the equation will become Ne into E into A into VE, where Ne is the number density of electrons, and this E is a electron charge, A is a cross-sectional area of the conductor, and VE is the drift velocity, similar to the one we had it for metals. Okay, yeah. Now similarly we can write the equation for conductivity or two holes. Okay, so we have two equations, equation 1 and 2. So total current in an semiconductor is due to both electrons as well as the holes. So I is equal to IE plus IH. So now therefore we can add equation 1 and 2, and you can just progressively view this one. I is equal to E into A into NEVE plus NHVH. Okay, and we know that J is equal to I by A. Then we can substitute that in this equation because you have I here and you have A here. So therefore that is I by A is equal to J, that you can write in the left hand side, and right hand side remains with the E into NEVE plus NHVH. Okay, we had that equation from the previous slide. Now divide both sides by E is the field, so it is on the left hand side J by E, and on the right hand side what we do is we keep that capital E within the bracket, so that you have the equation, because V by E is equal to mu, that is why. Okay, so the equation 4, in equation 4 what we have is J by A, E is what? J by A is sigma. Okay, that is sigma, and E by mu UE, VE by E is mu E. Okay, and VH by E is mu H. So we have on the left hand side E into NE mu E plus NH mu H. Okay, and that means for intrinsic semiconductors, we know that Ne is equal to NH, which we can also write it as Ni. So conductivity is given by, if we write sigma as sigma I for intrinsic semiconductors, then the Ne here and NH here are equal for a intrinsic semiconductors as per this equation. So we can replace that one as Ni and bring it out of the equation expression mathematically. So that becomes equation 5. Okay, and it is a equation for conductivity of intrinsic semiconductor. So let us again consider that equation 4, which is the total conductivity of a semiconductor. Now let us work for extrinsic semiconductors. Okay, extrinsic semiconductor. Now first let us consider N-type. In N-type, what do you mean? The number of electrons is more than number of holes. Okay, so apply that in equation 4. Then you are going to get for N type of semiconductors as sigma N. You write sigma as sigma N for N type, and capital N E into mu E. All of them refer to the electrons. Okay, and for extrinsic semiconductors with the P-type materials, what we have is NH is greater than Ne, or number of holes is greater than number of electrons. Apply that to equation 4. We have it as similar to above. Sigma P is equal to NH E into mu H. Okay, that is the expression for conductivity of intrinsic N-type that is P-type semiconductors. Okay. Let us go to one of the important experiments, which is called as Hall effect. The most striking experimental evidence leading us to the introduction of concept of positive current carriers or holes in crystal is furnished by a Hall effect experiment. When a conductor is placed in a magnetic field, for example, you could see here magnetic field, perpendicular to the direction of current flow. So that is this is the current flow, that is perpendicular. Magnetic field is perpendicular to the current flow. Then a voltage is developed across the specimen in the direction perpendicular to both magnetic and electric current. Okay, so that is what is interesting here. The voltage is called the Hall voltage. Okay, the voltage we call it as a Hall voltage, which is also represented as VH. Okay, this could be understood by Fleming's left hand rule also, wherein forefinger refers to magnetic field, middle finger refers to current, and the thumb refers to the thrust or Hall voltage. So this is the schematic picture. I have drawn it to explain a situation to get the expression for Hall coefficient. Now let us consider the current I that is carried out by electrons with charge minus E, for example. Okay, under the influence of magnetic field. So under the influence of this magnetic field, the electrons will be subjected to Lorentz force such that the lower surface collects the negative charges, as you could view here. Lower surface collects the negative charges and upper surface the positive charges. Here upper surface collects the positive charges. Ultimately, a stationary state is established along the y-axis. Okay, so that means along this axis, that is y-axis, as you could see here, this is as I have drawn it as x, y, and z. So in the y-axis, a stationary state is going to be established in which the current along y-axis vanishes and a field Ey is set up. Okay, a field Ey is going to set up. This is what the direction, as you could see here, and Ey is going to be there. Okay, it is known as Hall field. This is what we call as Hall field and represented as EH. It exerts upward force Fh on the electrons. If the current is carried out by the holes of the charge plus E, the upper surface would become negative and lower surface would become positive charge. That is, Ey would be reversed. Due to this, the Hall voltage measurement gives us the information about the type and density charge carriers, whether they are electrons or holes. Under such condition, the force exerted on the electron of charge minus E by a combined magnetic and electric force field is called as Lorentz, is given by Lorentz formula. This is the Lorentz formula, wherein you could see that F is equal to minus E into E plus 1 over C into V cross B. Okay, that is in CGS unit. And in the SI unit, if you write the same formula, there is a Lorentz formula, it will be F is equal to minus E into E plus V cross B. Okay, but in this case, mostly we proceed with the CGS unit here. Okay, let's proceed. So by applying the Lorentz formula to the above figure, so that means in this figure, if you are going to apply that, then we are having, because we are having the suffixes like Fy, because that is a Lorentz force developed along the y-axis, and E, you just compare this equation 1 and equation 2. The difference is just the subscripts. Okay, what is Ey? Ey refers to the electric field developed along the y-axis. Okay, and 1 over C. And Vx, what is Vx? Vx is the average drift velocity of electrons due to the applied current along x direction. Okay, cross Bz. Okay, that is nothing but applied magnetic field along z direction. Okay, and this first above equation is the same as the previous one in the previous slide. Okay, when the stationary state is established, as you could remember, a stationary state will be established with the negative side, negative charges accumulated at the bottom side, as you could see here, bottom side, and positive charges accumulated at the higher side, and we are going to have a field that is developed. That is, Ey is going to be developed. In such case, Fy is equal to 0. Okay, Fy will be 0. So then what happens to the equation 2? So because Fy is equal to 0, then you need to just write or rearrange 0 is equal to minus e and proceed on the right hand side. Okay, that is equal to, as you could see, a minus Ey is equal to minus 1 over c into Vx cross Bz. Okay, that will be equation 3. So now we know the current density Jx may be expressed as J is equal to minus N EVx. Okay, where N is a carrier concentration. Okay, since current is equal to, this is all we know from the previous one, I is equal to NEVD into A, and J is equal to I by A, or that is equal to NEVD. Okay, NEVD, that we can write. And Vx, therefore the Vx can be written as, if you just rearrange the previous equation, this equation, Vx is equal to minus Jx divided by Ne. Okay, then substituting that equation 4 in above equation 3, you are going to get the expression for Ey, that is equal to Jx Bz divided by NEC, that will be equation 5. Rearranging that equation 5, we are going to get this equation, that is Ey by Jx Bz is equal to Rh is equal to 1 over NEC. So then if you consider only the right side part of the equation, which we could rewrite as Rh is equal to 1 over Ne. Okay, that is in the SI system. Okay, so that we have the equation both in CGS and SI system. Okay, so where RH is nothing but the Hall coefficient, which is important for us. Okay, yes, this is what. So RH in the experiments, usually RH is determined by sign and density of charge carriers. If RH is negative for electrons and the RH is positive for the holes, that's all. Okay, so if you get RH as negative, then it is electrons. If it is RH is positive, then it is holes. Okay, so now if you consider the conductor of thickness D and width W, and then let us say that electric field E y is equal to Vy by D, and Jx is equal to Ix by W into D. W into D refers to the cross-sectional area. Okay, so that is the cross-sectional area of the I that is moving, here. Okay, so this is the cross-sectional area. Okay, fine. Okay, then substituting these two equations, that is Ey and Jx, in the Hall coefficient equation, wherein you have in the previous slide Ey by Jx into Bz is equal to Rh, then if you could replace the Ey and Jx of these two, then you are going to get Rh as equal to Vy into W divided by Ix into Bz. Okay, yeah, using the above equation, Hall effects can be calculated for a conductor of known dimension, because width, you can measure the width in keeping a definite magnetic field. This is what we are applying magnetic field, and current is also going to be applied. Okay, this is also going to be applied, but this is going to be measured. So Vy is going to be developed, because E is going to be developed, right? This Ey is going to be developed, that you can calculate by Vy. Okay, then Finally, by using the formula, you can get RH. Okay, and based on RH, you know in the previous slide, we can estimate also whether the conductivity is due to holes or due to electrons. From the above equation in the previous slide, we can get the expression for Hall voltage, that is VH, is equal to RH into Ix Vz divided by W, which these numbers and all you can understand better by referring the notes. Here you could view some of the RH values for a few materials, like lithium is having minus 1.89, so the electrons and number of charge carriers there. And for copper, for example, it is minus 6 into 10 to the power minus 24. Okay, so similarly you can, and this column refers to the SI unit. Here it is just SI unit, otherwise it is the same. So you can just estimate, you can just know the conductivity of electrons due to electrons or holes. And in the case of semiconductors, you could see that positive or negative values depending on the doping. That's what we know. If it is a doping is to form a p type, then it is holes. If it is for n type, then it is due to electrons.